Welcome back. So, in last lecture we were talking about that how the pattern of the earthquake, that is in terms of the recurrence, varies over the time because of the change in the rock strength, and this is exactly what has happened in 2015 Gorkha earthquake. So, Gorkha earthquake research carried out by different groups have revealed that not the complete stress was not released, that is the incomplete stress release was took place, and there is an expectation that in a short period there will be a major earthquake along the Himalayan frontal fault. Moving ahead, few more things which are important, which we were talking about in the previous two slides, and that is the site located from the source is important, type of faulting is important, and the overall tectonic framework is important, and mainly this is related to towards the reduction of the seismic hazard part. So, how far is my site located? Suppose for example, the section which has been the plan view which has been shown here is the dam, and from that dam how far is the faults, the active faults are located, and what are the different type of faults here. So, for example, if you take this map, it shows that there are two different type of faults which are located on either side, that is on the north and south of this dam. So, this is a strike slip fault, whereas this is a thrust fault. So, this what has been shown here, the symbol is of your strike slip fault, and this one is the symbol which has been shown as the reverse fault. So, two different type of faults exist close to the or at a particular distance from the dam, that is the site of interest. So, here it says that around 42 kilometers, and here it says that if the source is located here, then it is 32 kilometers. And further, another part is that even if you are having like the different mechanism, it may trigger different type of earthquakes and with different magnitude. So, 6.5 here consistent with the rupture length of 30 kilometers and slip of 1 meter, whereas here, and then in terms of the reverse fault, what we have is that is this is the section which has been shown A dash. So, this you are having A dash here, and this you are having A. So, towards the A you are having thrust fault, and towards A dash you are having strike slip fault. So, this is what has been shown here. So, you are having a strike slip fault here, you are having a thrust fault here. So, thrust fault is exposed at a particular distance, and a strike slip fault. So, a shallower earthquake and the magnitude is larger, the length is larger, and all that. So, these are all important parameters which are required for the seismic hazard assessment. So, what will be the slip, at what depth it will take place, and what will be the distance, and what will be the magnitude. So, this whole exercise has been done to understand the ground acceleration, that is the intensity of shaking. So, what will be the intensity of shaking at a particular location? So, as I have been emphasizing that this will depend on the geology of the area. So, the different material within the earth crust will have different ground acceleration. So, this is what has been shown here, that you are having this red is over here. So, probably this is an alluvium here which is showing the high intensity of shaking, and then shaking is lesser in the regions where they are having the harder rocks, or maybe the material which is not so loose. So, according to this also, one can make out that which area will have high or higher ground shaking as compared to the nearby areas, even though this whole area falls under the same city. Now, the rupture length is also having its relationship with respect to the earthquake, but as I told that we are going to now look at the primary evidence and the secondary evidence. Okay. So, primary evidence, for example, is your surface faulting on the fault or near the fault, and the secondary evidence are the evidences or the signatures where the area has been affected either by the landslide or liquefaction. Okay. So, even the far located areas will have secondary effects, and the left hand side of the figure, it shows that depending on the magnitude, okay, there will be an length of the rupture length will increase. Okay. So, for example, until 5 magnitude, this is what we call the threshold limit. Okay. No geological evidence will be evident because of the movement. Okay. But mostly no movement will take place if the earthquake of 5 magnitude is occurring in any particular region or on any particular fault, no displacement. But as you move up 6, 7, 8 and 9, then with, for example, 6, you can expect displacement along the fault up to 3 meters and up to 80 kilometer of rupture. And if you move about like 8.5 or so, then the rupture can extend up to 300 kilometers and the slip will be of 10 meters. So, I will just put in sketch here. So, what exactly they are talking about here is, suppose you have a landform that is in fault scarp here on the surface. So, there is a fault here. So, this slip along the fault is what has been talked here about, that 3 meters. So, slip, the movement along the fault plane. So, this is your fault plane, will be around 3 meter if with the magnitude around 8 to 8.5. Okay. So, this is the magnitude, and the rupture which we talk usually about along this line. Okay. So, this will be around the over 300 kilometers. So, this is what has been attempt has been made based on the historical data as well as paleoseismic data. Okay. And if you move further up, like around 9.5, the rupture may extend up to 1000 kilometers, and this was the case we had, like 9.3 magnitude earthquake of 2004 Sumatra, Andaman. Okay. And the rupture length was almost like 1300 kilometer. So, based on this also one can discuss out that what will be the amount of displacement one will expect, that is, if you are having the magnitude, and what will be the amount of or the length of the rupture along the fault, okay, on surface. So, one is on fault and along the fault. Okay. Now, taking into consideration the Indian subcontinent. So, we very well understand that the physiography of India is bounded from all sides, mostly in the northern side and the eastern portion and the western portion here. Okay. We have a major tectonic boundaries. So, major seismic events in India or Indian subcontinent mainly. So, we have one is the main zone is in the northern side, which has hosted several large magnitude earthquakes above 7.5. This starts from whatever the data we have. It of course, it goes up to 25 AD, but we don't have the data of in between because of either the loss of the records, because a lot of foreign people have invaded us, burned the records. So, we don't have much of the information available. Likewise, in other countries, for example, Japan, they have very consistent database in terms of such events, okay, catastrophic events, either it is tsunami or it is earthquake. They have very good data and written historical chronicles. So, in this we have the data from, like for example, few examples have been given here. 1885 Kashmir earthquake, magnitude 7.5, 1555 Kashmir earthquake, magnitude 7.5 or greater, then 1905 Kangra earthquake. These are all I was talking in the last lecture, that in 20th century we had almost 3 major earthquakes with greater magnitude of 7.5. Okay. And then we have the recent one is Kashmir, and then 2015 was Gorkha earthquake. So, Gorkha earthquake in 2015, and in 2 months period we had 2 earthquakes. So, one was the main shock, and this is considered as an aftershock or a triggered earthquake because of the stress transfer. So, the question comes that whether we have only those earthquakes which have been listed here have occurred in Himalayas. The answer is no. There are many more which remain unrecorded or which were recorded, but we don't have the data with us. Okay. So, the paleoseismology helps us in reconstructing those events which have occurred during historic time and prehistoric time, or we can say up to last 10,000 years. Okay. Then apart from the northern belt of Himalaya, one of the most seismically active zone, we have another one is Andaman Nicobar region, which has again revealed that they were these are all available in the records, historical records, that were major events in 1679 magnitude 7.5, 1762 magnitude 7.6, 1847, 1881, 1941, and then the last one which we experienced was 2004 Sumatra Andaman earthquake. So, like this whole belt in the north coming down to the south is the most active zone in terms of the seismicity in the Indian subcontinent. Apart from this, okay, if we move towards the west, then we have the Makran subduction zone. So, this is Andaman, Sumatra Andaman subduction zone. There is a collision, or we can say the subduction zone. Initially subduction took place, but now we are having the collision zone between the 2 continental plates. But here we are having oceanic plate subducting below the continental plate, and this is Makran subduction zone, again telling us the story that it had triggered earthquakes and associated tsunamis in 325 BC and 1945. Of course, the tsunamis which were been generated along this zone must have affected this whole region. Not only this, if you are having a mega tsunami similar to triggered by the magnitude similar to this one, that is 2004, then those tsunamis must have affected the many countries adjoining the Indian Ocean and even away from that. Whereas this area would have affected the whole region and the west coast of India. And then we have another zone which is the most active relative to what we see in Himalaya and Andaman, is the Kutch region, which has hosted earthquakes during historical time. One is 893, 1668, 1891, 1845, 1956, and the most recent one is your 2000 11th fault. The magnitude was 7.8, and nobody expected that there will be an earthquake in 2001, and so because we never did and complete, or we never did studies in detail in that region. Very few groups from India were working in this region, but now what we see is that we may have much larger magnitude earthquake than what we have experienced here, okay, maybe around 8. So this is what where one can talk, or they can give the input after having a proper paleoseismic studies. Similarly, this goes for the Himalayan region, where we have whatever the information we are having is not complete, and we are not even sure that which fault was responsible for triggering the particular earthquake. Okay. For example, we based on the paleoseismic studies, we have been able to tap or narrow down the 1905 earthquake did not occur on the Himalayan frontal fault, but it occurred way behind, 100 kilometers way behind, on a new fault, on Kangala Valley fault. And then similarly, these two events, the groups or research groups have identified that they took place on the Himalayan frontal thrust. But we will have more discussion on this part when we are moving ahead in this course. Now, coming down to the paleoseismology part, what exactly we will do, we will slowly start learning and in this about the paleoseismology, and what techniques and what are the steps which we are going to adopt to get the best results. Okay. Now, before we get into all this, it is important for us to understand few terminologies related to recovery of fault activity. So, we have in broader sense, we have the geological time scale, which has been divided in era, period and epoch. So, for example, we take this is the Cenozoic era is the most youngest era in the geological time scale, and we are interested in Cenozoic part. Okay. And even with the Cenozoic, we are more interested in the Holocene epoch. Okay. So, one is you have the era, then you have period, then you have epoch here, and then this era is the Cenozoic, and Cenozoic era comprises two. One is the Quaternary and Tertiary. And why Tertiary? Because the research tells us about that this was the period when the collision started, that is collision between the Indian plate and the Eurasian plate. So, on the regional scale, or we can not regional, but on the global scale, if you want to understand the tectonic framework, then this period is important for us to be considered, because this was the time or the initiation of the deformation that started along the Himalayan region, or the formation of the Himalayas started. Coming to the Quaternary period, of course, a lot of climatic fluctuation were been observed during the Pleistocene epoch, and then coming down to the Holocene epoch, which is ranging up to 10,000 years, and that period, and during that period any activity has taken place along the fault, then we term that as an active fault. And any activity which were recorded during the Pleistocene period or Pleistocene epoch are considered to be the potential active faults. Okay. So, this is what we need to understand, and probably the faults which were formed during Tertiary or beyond that, that is pre-Cenozoic time, or further, that is in terms of the age, if you take, that is before 16,50,000 years, okay, before, then we consider those faults as an inactive faults. So, this portion of the part is extremely important before we get into the real paleoseismic domain. Okay. So, I will stop here and we will continue in the next lecture talking more on paleoseismology. Thank you so much.